In the previous lectures, we talked about what is the content of this course, and while we were talking about the content of this course, we gone through the certain number of questions that we will be trying to address in this particular course. So, what is formal languages? What is automata? And what is theory of computation? Then we also talked about different things like the basic model of computation, how string represents computation models, and so on. Then we tried to answer some of the basic questions like what is computation and what are computational devices that we have worked upon. These are the things that we have already talked about. Now, in this particular course, we also will discuss the different computational devices. We will discuss different computational devices based on their resources. So we will be trying to talk about that. So what are the different computational devices, and we will describe them on the basis of their resources. And then now we are going to talk about something called finite automata. So we are going to talk about this finite automata. This is the simplest computational device that we are going to talk about. By automata, we mean a machine, and then we talk about finite. So finite actually refers to the finite number of resources, and in fact this resource is nothing but a memory. So we say that it requires finite memory or finite number of states, which ultimately means that the number of states cannot be increased arbitrarily by, or it cannot depend upon the number of or the input size, number of inputs or the input size. So basically we cannot increase or decrease with the number of inputs. We cannot do that. So in other words, it actually means that not only it has finite number of states, it can only memorize finite number of things. So the only previous state may be remembered, or only some previous states. The finite number of previous states can be remembered. It cannot be possible that you remember a lot of things. So that is where the finite automata is there. And let's try to discuss some examples of the machine. So consider an electric switch or a toggle button. So there is an electric switch with a toggle button. If you are at state off and you push it, you reach to state on. So you reach to state on. Reach to state on. Okay, and reach to state on. And if you push back on this state on, you will reach to state off. So here you also push, here you also push. So if you start at state off and you push it even number of times, you will end up at state off. And if you start at state off and you push the button all number of times, then you will end up at on state all number of times, push odd times, starting from state off. Right? And you can reach at off state after pushing even times. And starting from state off. So basically these are the two things. So we can reach here or here. So there are two things that somebody can talk about. If I give you a sequence of actions, where you will land up if I start at a particular state, or what is the sequence of states that will be achieved if I give you a certain sequence. So let's talk about another example, which is of a time regulator. The speed of time is proportional to the state number. For example, it means that if you are at state 0, the fan is off and is stopped. If you are at state 1, then fan is running slowly, and if you are at state 2, then fan is running a little bit faster, and if you are at state 3, fan is at its full speed. So there could be two types of actions that I can take. Initially, in the previous question, we have only one action, that is push. Now, in this particular problem, you have two different kind of actions possible. That is, you can move from state 0 to state 1 by taking an action corresponding to clockwise direction, right? And from 1 you can move towards 2 by again choosing a clockwise action. Similarly, from 2 to 3 you can again choose a clockwise action. From 3 to 0 you can again choose a clockwise action. While on the another part, from 0 you can take another one. You can take another action that is called anti-clockwise action. So you can move in this particular direction while taking anti-clockwise movement. And from 3 to 2 you can again take anti-clockwise action. From 2 to 1 you can take anti-clockwise action. And from 1 to 0 as well you can take an anti-clockwise action to move from 1 to 0. So if you possibly start at 0 and let's say you choose a sequence of actions A, C, then where you will reach. So starting at state 0, if I choose A, then I will land up at 3. Then again if I choose A, then I will land up at 2. And if I choose a C, then I will land up at 3. So how it is going? We reach to a state 3. On the contrary, if somebody wants to know about the sequence of states, so we can talk about the sequence of states. So for example, initially we are at 0. After taking an anti-clockwise action, we reach to state 3. Another anti-clockwise action, we reach to state 2. And then another clockwise direction action, we reach to state 3. So in this way, we can talk about the two different versions where we will reach after consuming or after taking the sequence of actions. Where we will reach? So we will reach at state 3. And what is the sequence of the state with the help of which we have finally reached to state 3 with this particular sequence of actions is 0, 3, 2, 3. So these are the two things that we can ask or we can talk about as of now when we talk about this particular kind of automata. So as an example, you can try out these two things. So if you are at state 3 and you have possibly two different types of actions, clockwise action, anti-clockwise action, and if you choose this particular sequence, where at what particular state you will reach in, and if you take this particular action sequence, then where you will end up, that you can try to answer by yourself. Let's take another example. The example is of binary strings, and we are interested in the binary strings that are made up of zeros and ones, and we want to know whether the binary string is divisible by 4 or not. So anyways, we know that any number, if divided by 4, it will result into either a remainder 0 or a remainder 1 or a remainder 2 or a remainder 3. There could not be any other possibility. So if you have a binary string, you can actually land up at either 0 remainder or 1 remainder or 2 remainder or 3 remainder. Right? So for example, let's talk about some binary strings. So let's say that this is one binary string. Now the decimal equivalent of this binary string is 0. And is it divisible by 3? Yes. So why? Because if I divide 0 by 4, then the remainder remains 0. So it is divisible by, yes. So it is, yes, divisible by 0 because the remainder is 0. Let's try to consider 0, 1, 1. The decimal equivalent is 3, and we see that it is not divisible by 3. So the remainder is 3 and it is not divisible by 4. Let's talk about 1, 0, 0. So which is a 4, right? And yes, it is divisible by 4, and that's yes, it is divisible. So that's what we want to discuss over here. Now let us try to understand how it happens. Can you just think about it, that if I know that what is the remainder currently, so let's suppose the current remainder is 0. So let's say I have a string, I have a certain string, and up to here I have consumed, I have already processed, and this part, the rest of the part, I am actually trying to do. So this part I am trying to do. So when I am trying to do this part, I want to know what is the remainder previously. So let us suppose that the previous remainder is 0. Now if I got a 1, so the new number will become 0, 1, right? Which is actually 1. So the remainder will be 1. So the remainder will be, in the new situation, the remainder will be 1. And let's suppose if I get a 0, then what I'll be having, the remainder will remain 0. So here the previous digit or bit was 0 and the new bit is 0. So the remainder of 0, 0 is 0. So basically we will reach the same state, right? Now consider at 1. If I get 1, if I take 1, so let's suppose if I get 1. So what is the remainder? So earlier it was a remainder 1 and now you get a 1. So the last bit, you can assume it is like this, so that the last bit is 1 or last remainder is 1, and you shift this last number or whatever number over here, you shift it by to the left side and append a 1 over here. So definitely it becomes 3. If you take this becomes 3, then the remainder will be 3. And let's suppose if you get a 0, because it becomes 1, 0. So earlier the remainder was 1. Now you shift it left. So this becomes 2, and then you append a 0. So that becomes a 2. So your remainder is now 2. Now again we can actually go ahead with the 3. So what will happen? If there is 3, the equivalent of 3 is 1, 1. Equivalent of 3 is 1, 1. And now if I append 1 over here, it becomes 7. So if I have 7, what is the, so 7 modulo 4? It becomes what? That is 3. So if I get a 1 over here, I'll end up within the same state. But if I get a 0 over here, then 0 over here. So if I write here, so I'll reach to state 2. Okay, state 2. Now let's try to consider at state 2. What will happen? At state 2, if I take a 0, so state 2 is actually the remainder 2, it can be written as 1, 0. And if I take 0 over here, so that becomes 1, 0, 0. 1, 0, 0 is equivalent to 4. And if I take the modulo 4, it is 0. So we'll reach to from 2 to state 0 by taking or by consuming this bit 0. And from 2, if I take 1, so initially the remainder is 2, which has the binary equivalent to be 1, 0. And if I add 1, append 1, so it becomes 5. And if it is 5, so 5 modulo 4 becomes 1. So you will reach to state 1. After taking 1. So ultimately that will be the entire set. So either you can have a state 0 or the remainder 0, or possibly you can have a remainder 1, or you can possibly have remainder 2, or possibly have remainder 3. But you cannot have any other remainder when you divide it by 4. When you divide any number by 4, you can have remainder 0, 1, 2, 3. So ultimately the previous remainder is important. So you see, only the previous remainder is important. The entire number does not have any relationship with the next state. If I keep dividing with 4 and trying to get the remainder, so the current, or since I am reading the entire string one by one, so if you have, let's say, 1 0 0 1 1 0, so I am reading the bits one by one, and as soon as I am reading one by one, so up to the current bit I am trying to find out what is the remainder. And in that process, I am trying to reach to a particular state which tells me what is the remainder up to this digit, up to the current digit. So if I reach to that current digit remainder, then when I move or when I append one more bit, let's say I appended one more bit, then where I will reach. So since the computation is saying that the previous string or the prefix of this string is telling me the remainder, and this new bit or the next bit is telling me the possible action. So okay, if I have one added, then I will get the remainder only out of these 4 states only. So earlier, in the earlier possibility, I have, so while processing the previous string, I will be reaching to some state from 0, 1, 2, 3, 4, and if I append one more bit, I will be reaching only on these states, only one of these states. So definitely I do not have any problem in discussing this entire thing with the 4 states. 4 states corresponding to the remainder corresponding to the remainder of 4. So that's what we can see. So that is how we can build up a finite automata related to divisibility by 4. So let's try to understand what are the specific or what are the special states. So the special state is, one of the special states is because we want to know whether the number is divisible by 4 or not. So here we see that the number is divisible by 4 if the remainder is 0. If the remainder is 0. So this is somewhat a special state in that sense. Because if I reach here at state 0, I'll say that the number is divisible by 4. So that's how it works. Now you can try it out. What will happen if we start at state 0, 0 and we get 1, 1, 0 as our string. So what sequence of states we will be getting and where we will end up, whether this number is found to be divisible by 4 or will not be found as divisible by 4. So that one can answer. In the next video, I'll end up this particular video, and in the next video we'll be considering more examples on finite state automata. Thank you.